We're working on the lab Acceleration is Change. I had constructed an accelerometer, which is made out of a jar that's got a paper clip tied to a thread taped to the bottom of the lid. And whenever the paper clip and thread move, that indicates acceleration is occurring, which means that there is a change in speed, direction, or both on the accelerometer. Now, in this particular lab, you are asked to do a variety of things with your accelerometer and report back if you observe acceleration, are the forces balanced or unbalanced, and then draw a free body diagram for it. The first two situations, starting the jar moving, so pushing on the jar and causing the jar to accelerate. This was done in the prior lab, and in it you observe when your hand is on the jar and speeding the jar up, the paper clip swings back toward your hand. Because the paper clip is moving, that means there's acceleration. Because there's acceleration, it means forces are unbalanced. I had drawn this free body diagram previously. As I had mentioned, in a free body diagram, the object is represented with a square, and then arrows are used to represent the forces. If in this situation I'm pushing the jar from the right, we see the arrow labeled force applied. What is opposing the force applied? It's the force of friction supplied between the bottom of the jar and the top of the countertop. Notice that the arrow for the force of friction is smaller than the force applied. If I'm accelerating and it's going in this direction, it means that the force of friction is less than the force applied. The upward arrow represents the normal force, which is supplied by the top of the countertop, and then that is opposed by the force of gravity. In the second situation, you are to observe the jar coming to a free sliding rest. Again, you do see the paperclip move. It swings out away when the jar comes to a stop, which, by the way, slowing down is acceleration. And then the string and the paperclip swing back to its original vertical position. A free body diagram for this would look like what I have on the board here. Again, I've got my square representing the jar. The normal force is being opposed by the force of gravity. Since my hand is no longer on the jar in this particular instance, I don't need an applied force, and all I've got is the force of friction. On the next situation, I'm asked to move the jar in a straight line at a constant speed. When I do this, I observe that the paper clip just stays straight up and down in a vertical position. This would indicate that there is no acceleration. Since there is no acceleration, the forces must be balanced. Now, what would this look like for a free body diagram? I'm just going to modify one that I've got here. I would have the normal force and the force of gravity equal arrows because they were equal but opposite forces. And then I've got the force of friction and the force applied. And I did my best to make these two arrows equal in length but opposite in direction. So all the arrows are equal, showing that the forces are balanced. There is no acceleration. Next up, I've got the jar is at rest. I noticed that the paperclip is straight up and down. It's not wiggling. Since the paperclip isn't moving, this would indicate that all of the forces are balanced on it. There is no acceleration. What would this look like for a free body diagram? Well, once again, I can modify my diagram. I will have no force of friction. I will have no applied force. I've just got my normal force and my gravitational force that I want to include in this particular diagram. And then the very last one asks you, well, what happens if I move the jar in a circular motion at a constant speed? Now, constant speed, right? Speed's not changing, but the direction is. And because the direction is changing, I observe my paperclip swinging out in an arc. This means that yes, there is acceleration and the forces are unbalanced. For this very final diagram, we're not actually drawing a free body diagram. You're asked to draw this from the top down, a bird's eye view, as if you were looking through a see-through lid. So I'm just going to give little snapshots in time here as to what this would look like. When the jar is going this way, I see the paperclip swinging out in that direction. I see the paperclip swinging out in this direction, the paperclip swinging out in this direction. So if I were looking top down and the lid were see-through, I would notice the paperclip swinging out in an arc. Forces are unbalanced. And that's it for our lab. Acceleration is change.